When students have mastered using compensation to subtract one digit from two digits, they are ready to begin to generalize the use of this strategy to multi-digit subtraction, starting with subtracting two-digit numbers from other two-digit numbers. First, let's recall that difference refers to the meaning of subtraction in numeration, and distance refers to the meaning of subtraction in magnitude. Compensation involves keeping a constant difference or distance. We know that when we have two groups of objects, as long as we add or subtract the same number of objects to each group, the difference between the two groups does not change. It stays constant. We also know that any given distance, say 3 for example, stays the same regardless of its position on the number line. As the distance moves around the number line, the numbers that it is between each increase or decrease by the same amount. This is constant distance. Finally, let's recall that subtraction is not commutative. Order matters in subtraction. A minus B is not the same as B minus A. It is important by now for students to know the correct terminology for subtraction. The minuend is the number we are subtracting from. The subtrahend is the number we are subtracting. As we saw in stage 14, we want to find the nearest 10 to the subtrahend and use compensation to create a 10-friendly number sentence that's easy to solve. We find the nearest 10 to the subtrahend because 10s are easy to subtract. For example, if we are subtracting 19 from 96, the subtrahend is 19. The nearest 10 to 19 is 20. We know that if we add 1 to 19 to make 20, we also must add 1 to 96 in order to keep a constant difference or distance. Thus, we have shown that 96 minus 19 is the same as 97 minus 20. Now we have a 10-friendly subtraction problem, and we can subtract 20 from 97 without regrouping. Thus we know that 96 minus 19 is 77. We want to guide students to the understanding that subtracting 9 ones from 6 ones will always produce 7 ones regardless of the decade that the minuend and subtrahend are in. In every case, we can create a 10-friendly equation by adding 1 to both the minuend and the subtrahend. Then, it is just a matter of subtracting the 10s and adding 7 to obtain the difference or distance. In fact, whenever we are subtracting 9 ones, we add a 1 to the minuend and round the subtrahend up to the next 10. So if we are subtracting 9 ones from 2 ones, the difference or distance will always have 3 ones. If we are subtracting 9 ones from 8 ones, how many ones do you think the difference or distance will have? We know that we will need to add 1 to the minuend, and so the difference or distance will always have 9 ones when we are subtracting 9 ones from 8 ones. When we are subtracting 8 ones, we know that we will need to add 2 to the subtrahend in order to reach the nearest 10. That means we will also have to add 2 to the minuend. In this case, we can show that 94 minus 48 is the same as 96 minus 50. Now we have our 10-friendly equation, so we can see that the difference or distance in this case is 46. When we are subtracting 7 ones, we know that we will need to add 3 to the subtrahend to reach the nearest 10, so we will also need to add 3 to the minuend. In this case, we can show that 95 minus 57 is the same as 98 minus 60, so the difference or distance is 38. If the subtrahend contains 6 ones, we know we will need to add 4 to get to the next 10, so we will also have to add 4 to the minuend. In this case, we have shown that 95 minus 56 is the same as 99 minus 60, so the difference or distance is 39. We saw in stage 14 that compensation always works, but it is not always the most efficient strategy. In this case, we would need to add 4 to the subtrahend and minuend to get the 10-friendly equation 100 minus 60. This is very easy to solve. We can immediately see that the difference or distance is 40. However, we could have used our knowledge of number composition to eliminate the sixes and subtract 90 minus 50 to obtain 40 in one step. In cases where the minuend contains more ones than the subtrahend, compensation will usually not be the most efficient strategy. In this case, we can show that 97 minus 56 is the same as 101 minus 60. In order to do so, however, when we added 4 to 97, we cross not only a decade, but 100. That means we had to regroup not once, but twice to add 97 plus 4 and obtain 101. In such cases, it will usually be more efficient to use the partial differences strategy. Partial differences involve subtracting place value units separately and then combining these partial differences to obtain the whole difference. For example, in our problem 97 minus 56, first we can subtract the tens, 90 minus 50, to obtain 40. Then we can subtract the ones, 7 minus 6, to obtain a partial difference of 1. When we combine the partial differences, the whole difference between 97 and 56 is 41. Being able to determine whether it is more efficient to use compensation or partial differences depends on an understanding of the concept of unitizing, or using digits to count groups of items as well as individual items. In this example, we have 99 in the 10-frame place value mat, and we want to subtract 17. Notice that we have more ones in the minuend than we want to subtract, so we will not need to regroup. We can simply take the 7 ones that we need and the 110 that we need to see that 99 minus 17 equals 82. Whenever we have more ones in the minuend than we need to subtract, we can use partial differences. In this case, 90 minus 10 equals 80, 8 minus 7 equals 1, and 80 plus 1 equals 81. If we take the 7 ones that we need and the 110 that we need, we can see that we are in fact left with 81. In this example, we are subtracting 17 from 97. By now, we should know that when we have the same number of ones in the minuend and the subtrahend, we can solve in one step. We need not consider the 7 ones. We can simply subtract 10 from 90 to obtain a difference of 80. Now let's consider the example of subtracting 17 from 96. In this case, the subtrahend is calling for more ones than we have available in the minuend, so we know we will need to regroup. We can create an equivalent 10-friendly equation by adding 3 to the subtrahend and the minuend. That would give us 99 minus 20, which would be 79. However, let's pause for a moment to recall from stage 14 the relationship between the number of ones in the subtrahend and the number of ones in the minuend when regrouping is required. Because the difference between 6 and 7 is 1, we know that when we take the 6 available ones from the minuend, we will need one more 1 to make 7. To get that 1, we must ungroup a 10 to recreate 10 ones. When we take the 1 we need to make 7 with 6, we will be left with 9 ones. Now we must subtract the 10 that we need for the subtrahend from the remaining 8 tens in the minuend, and we can see that the difference between 96 and 17 is indeed 79. Let's consider one more example where regrouping is required. In this case, we are subtracting 17 from 95. Can you use compensation to find an equivalent 10-friendly equation? The nearest 10 to the subtrahend is 20, so we must add 3 to the minuend and the subtrahend to obtain a 10-friendly equation of 98 minus 20, which would be 78. We can also see that the difference between the 5 ones in the minuend and the 7 ones in the subtrahend is 2. So we should have 8 ones after we complete the subtraction because 8 makes 10 with 2. First, we take the 5 ones available in the minuend. Then we ungroup a 10 to recreate 10 ones. We need 2 of those ones to make 7 with 5. Now we need to take a 10 from the remaining 8 tens, and we see that 95 minus 17 is, as we expected, 78. We can help students learn to use 10 to simplify subtraction by giving them pairs of problems in which the differences make 10. For example, we can subtract 0 from 2 without regrouping to get a difference of 2 ones. That means when we subtract 2 from 0, we will need to ungroup a 10 and we will get 8 ones. We can subtract 2 from 4 without regrouping to get a difference of 2 ones. So when we subtract 4 from 2, we will need to ungroup a 10 and we will get 8 ones. We can subtract 3 from 5 without regrouping to get 2 ones. So when we subtract 5 from 3, we will need to ungroup a 10 and we will get 8 ones. If necessary, we can use the inverse relationship between addition and subtraction to help students fully understand the essential role of 10 in regrouping. For example, we subtracted 40 from 72 to obtain a difference of 32 without regrouping. Therefore, we can also add 32 and 40 to obtain a sum of 72 without regrouping. We subtracted 42 from 70 to obtain a difference of 28 with regrouping, which means we can also add 28 and 42 to obtain a sum of 70 with regrouping. We subtracted 32 from 84 to obtain a difference of 52 without regrouping. That means we can add 52 and 32 to obtain a sum of 84, also without regrouping. When we subtracted 34 from 82, we had to ungroup a 10 in order to obtain a difference of 48. That means when we add 48 and 34, we will have to create or unitize a 10 in order to obtain a sum of 82. When we subtracted 53 from 95, we did not need to regroup in order to obtain a difference of 42. So if we add 42 and 53, we will not need to regroup in order to obtain a sum of 95. When we subtracted 55 from 93, we were subtracting 5 ones from 3 ones, which meant we needed to ungroup a 10 to obtain a difference of 38. So if we add 38 and 55, we will need to unitize a 10 when we add 8 ones and 5 ones in order to obtain a sum of 93. Another effective strategy for helping students understand regrouping and subtraction is to give them strings and sprints of subtraction problems in which the differences all contain the same number of ones. For example, in this set of problems, all of the differences contain 4 ones. Can you find a pattern in this set of problems? Here's a hint. There are 2 basic ways to get a difference containing 4 ones. One way to obtain a difference of 4 ones is to have a minuend which has 4 more ones than the subtrahend. For example, 5 is 4 more than 1, and 7 is 4 more than 3. The other way to obtain a difference containing 4 ones is when a subtrahend is 6 greater than the minuend. For example, 6 is 6 more than 0, 7 is 6 more than 1, and 9 is 6 more than 3. Understanding this pattern opens up the possibility of using partial differences to solve all 2-digit subtraction problems, even those that involve regrouping. For example, we know that when we subtract 6 ones from 0 ones, we will have to ungroup a 10. And when we take the 6 ones that we need from that 10, we will be left with 4 ones. But we could get the same result by subtracting the difference in ones rather than adding it. We can generalize this strategy by saying that whenever regrouping is required, we can subtract the difference in ones from the difference in tens. 70 minus 40 equals 30. The difference in tens is 6, but regrouping is required, so we subtract the 6 rather than add it. Alert students may notice that finding the difference between 30 and 6 requires regrouping. However, because we know all the ways of making 10 by heart, we do not actually need to regroup to find this difference. When regrouping is not required, because there are more ones in the minuend than called for by the subtrahend, we use partial differences as usual. 80 minus 30 equals 50. 5 minus 1 equals 4. We add the partial differences together to obtain a difference of 54. When we are subtracting 27 from 91, we know that regrouping will be required. So we can use partial differences. 90 minus 20 equals 70, but we must subtract the difference in ones, which is 6, to obtain a difference of 64. We have seen that a deep understanding of the crucial role of 10 in regrouping allows us to use partial differences to solve any two-digit subtraction problem. When we use the partial differences strategy without regrouping, we add the difference in ones to the difference in tens. In order to use the partial differences strategy when regrouping is required, we must subtract the difference in ones from the difference in tens. It is essential that students understand these two cases of the partial differences strategy rather than simply learning them as a trick or a rule. We can assess this understanding using a simple subtraction table for the digits 0 to 9. Can you find all of the ways of obtaining 7 ones in a difference? Let's begin by listing them. First, let's show the ways of obtaining 7 ones without regrouping. In each of these cases, the minuend is 7 larger than the subtrahend. Now, let's show the ways of obtaining 7 ones with regrouping. In each one of these cases, the subtrahend is 3 larger than the minuend. This is because 7 makes 10 with 3. Now let's return to our subtraction table. We can see that the bright green diagonals show us all the ways of obtaining a difference with 7 ones. 7 minus 0, 8 minus 1, 9 minus 2 are all cases in which regrouping is not required. 0 minus 3, 1 minus 4, 2 minus 5, 3 minus 6, 4 minus 7, 5 minus 8, 6 minus 9 are all cases in which regrouping is required. There are some important patterns to notice in this table. First, notice that there are 3 ways of obtaining 7 ones without regrouping, and 7 ways of obtaining 7 ones with regrouping. Just as we saw in stage 17 for two-digit addition, the number of ways of obtaining any particular digit in the ones place without regrouping added to the number of ways to obtain that digit with regrouping will always equal 10. For example, notice that there is only one way to obtain 9 ones without regrouping, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9 ways to obtain 9 ones with regrouping. We can see that there are 1, 2, 3, 4, 5 ways to obtain 5 ones without regrouping, so there must be 5 ways to obtain 5 ones with regrouping. We can confirm this prediction. 1, 2, 3, 4, 5. Notice that the diagonal from 0 minus 0 to 9 minus 9 shows all the ways of obtaining a difference with 0 ones. None of these 10 ways of obtaining a difference with 0 ones involves regrouping. Below that diagonal are all the ways of obtaining a given number of ones without regrouping, And above the diagonal are all the ways of obtaining a given number of ones with regrouping. The minus signs above the diagonal indicate that if we are using partial differences, we must subtract the difference in ones from the difference in tens in these cases. Of course, they also indicate that these differences are negative numbers, but it is not necessary to introduce that concept at this stage. In conclusion, we have learned 3 ways to solve 2-digit subtraction problems. First, in cases where the minuend contains more ones than the subtrahend, we can use simple partial differences. The difference between 70 and 40 is 30, and the difference between 6 and 3 is 3, so we add 30 and 3 to get a difference of 33. In cases where the subtrahend is calling for more ones than are available in the minuend, we can use compensation to create a 10-friendly equation with the same constant difference. For example, the nearest 10 to 38 is 40. So if we add 2 to the minuend and subtrahend, we get the 10-friendly equation 86 minus 40, which gives us a difference of 46. If we have a deep understanding of the role of 10 in regrouping, we can also use partial differences in cases where the number of ones called for in the subtrahend is greater than the number of ones available in the minuend. Because we know we will need to regroup in these cases, we will subtract the difference in ones from the difference in tens rather than adding them. The difference between 90 and 30 is 60, and the difference between 2 and 5 is 3. 60 minus 3 gives us a difference of 57. Students who master all 3 of these strategies will have a tremendous advantage in constructing the meaning of multiplication. They will also have an advantage in solving the wide variety of word problem types that involve differences and distances. Because they will be able to perform the operations of subtraction easily, they will be free to focus their attention on the structure of the problem.